Thank you for joining me again for some more reinforced concrete design. Today we will be discussing the design of vertical shear in reinforced concrete sections. Shear occurs in all beams and slabs. Small amounts of shear can be dealt with by concrete in the section and tensile reinforcement. Examples of structural elements that develop low shear include lintels and slabs. More significant amounts of shear require at least minimum shear reinforcement, and high shear requires fully designed shear reinforcement. The state of stresses in reinforced concrete are complicated. Therefore, semi-empirical solutions are still used in design. Shear in a reinforced concrete beam is carried by concrete in the compression zone, aggregate interlocking in concrete, longitudinal reinforcement via dowel action, and shear reinforcement. In a beam without shear reinforcement, the concrete in compression zone carries between 20 to 40% of shear. Aggregate interlocking in concrete takes around 35 to 50%, and dowel action takes between 15 and 25%. Loaded beams develop vertical and diagonal cracks. The vertical cracks develop due to bending in the zones of high bending moment, while the diagonal cracks develop due to the action of shear in the zones of high shear forces. The diagonal cracks can start as vertical cracks. Beams can fail in bending or shear depending on the shear span or A to D ratio, where A is the distance between the vertical external loads causing shear and D is the effective depth of the section. Large shear span ratios are characteristic of long and shallow beams, which can resist only small shear forces. Low shear span ratios are characteristic of short and deep beams, which can resist large shear forces through arching action. We are going to consider 5 types of failure. 4 failure types are characteristic of beams without shear reinforcement, and they depend on the shear span ratio. The 5th type is characteristic of beams with shear reinforcement. Type 1 shear failure occurs in beams with a shear span ratio larger than 6. In such beams, bending moment is large compared to shear force. The failure mode is close to pure bending. In the shear zones, vertical bending cracks bend to form diagonal shear cracks, and with increased loading, one crack reaches the compression zone, after which parts of the beam on either side of the crack begin rotating around the compression zone. Eventually, the beam fails by crushing in the compression zone. Type 2 shear failure is characteristic of beams with a shear span ratio between 2 and 6. In such beams, the initial bending cracks incline at a lower load. The failure occurs suddenly by horizontal splitting along tension reinforcement, caused by the dowel action of reinforcing bars. This splitting reduces shear resistance of the beam due to the loss of bond between concrete and reinforcement. The horizontal crack connects with a shear crack, which reaches the compression zone, causing failure. In this picture, you can see a typical crack developed at failure in a beam with a shear span ratio between 2 and 6. Type 3 shear failure occurs in beams with a shear span ratio smaller than 2. In such beams, bending cracks do not develop. Instead, a shear crack suddenly appears across a complete section, which is followed by failure in the compression zone. Type 4 shear failure occurs when the shear span ratio equals 0. In this case, the structure fails in punching shear mode. This failure mode can occur in beams when the high load is very close to a support. High shear force causes failure at a vertical line between the load and support, or between shear links when they are present. Punching shear can also occur in flat slabs at connections with columns. Additional horizontal or inclined reinforcement can increase resistance to punching shear. Type 5 shear failure occurs when shear reinforcement is present. In such beams, links, or bent-up bars, intercept shear cracks and take shear force. The shear design should assure that the pitch of shear reinforcement is small enough to intercept all shear cracks. The ultimate limit state design for shear assumes that steel in shear reinforcement yields at failure. Eurocode 2 recommends the variable strut inclination method for vertical shear design. This method is based on an equivalent truss model and allows us to seek economies in the amount of shear reinforcement that we provide. These economies are achieved at the expense of additional curtailment and anchorage lengths of tension steel. To understand how this method works, let's consider part of a beam at a support. We're going to try and transform this beam into an equivalent truss. It should be noted that the members in the truss should be seen as smeared into the beam. Under gravity loads, the top beam will be in compression, which is similar to a top chord in a truss subjected to similar loads. The bottom of the beam will be in tension, which again is similar to a bottom chord of a truss. The reaction force at the support results in the development of shear in the beam. Since shear cracks are inclined, the reaction force is resisted by an inclined concrete strut. The strut is in compression and represents the first compression diagonal in the truss. The compression forces in the strut work to separate the top and bottom of the beam. This action is resisted by the vertical reinforcement. The combined action that this reinforcement represents is the first tension tie in the truss. The tension in the reinforcement is resisted at the bottom of the beam by a second inclined compression strut, which represents the second compression diagonal of the truss. The compression in the second strut is resisted by the tension in the vertical reinforcement, which represents the second tension vertical in the truss. Further inclined compression struts and tension ties can be identified in a similar way. Where shear is lower, the compression struts can have a lower inclination angle. According to Eurocode 2, the inclination of the compression struts can vary between 22 and 45 degrees. We can now summarize the discussion of the variable strut inclination method, which assumes that the beam behaves like a smeared truss. In this model, concrete acts as struts carrying compressive forces, while shear reinforcement acts as ties carrying tensile forces. The inclination angle of the struts varies depending on the shear force to be carried. In the zones of high shear, for example near supports, the angle theta approaches 45 degrees, and therefore cotangent theta approaches 1. In low shear zones, for example away from the supports, the angle theta approaches 22 degrees, and therefore the cotangent of the angle approaches 2.5. It is economical to find a theta appropriate to the situation in the beam. It is assumed that in T-beams, vertical shear is carried by a rectangular section, while the flanges are disregarded. This assumption is supported by experimental evidence. As you can see in the picture on the right, the flanges develop vertical bending cracks, while the web develops diagonal shear cracks. In the truss model, links and struts carry all the shear. The formulas used in the design for vertical shear are generally based on forces rather than stresses. The application of the truss model for the shear design results in additional tensile forces applied by inclined compression struts to tension reinforcement. The vertical shear design is based on 3 parameters, including VRDC, which is the design shear resistance of a member without shear reinforcement, VRDS, which is the design value of shear sustained by yielding shear reinforcement, and VRD max, which is the design value of maximum shear force sustained by a member. VRD max defines the strength of the most loaded inclined compression strut, while VRDS defines the strength of the tension ties. Let's see how the formulas for calculation of VRDS and VRD max are derived. To derive the formula for the calculation of VRD max, we need to consider the equivalent truss model. The maximum compression force that the inclined concrete strut can carry can be found as the design compression strength of concrete times the cross-section area of the strut. The design compression strength of concrete equals the characteristic strength divided by the partial safety factor for concrete. The cross-sectional area of the strut equals the breadth of the beam times the width of the strut, where the width of the strut is assumed dependent on the effective depth of the section. The force developed in the inclined compression strut from the applied loads can be found considering that the vertical shear force, VED, is its vertical component. Therefore, the compression force in the strut should be equal to the vertical shear force divided by the sinus of the inclination angle theta. In order to compare VRD max directly with VED, the maximum compression force in the strut is multiplied by the sine of the inclination angle theta. The expression for VRD max can be represented in different forms, as shown here, using algebra manipulations. Eurocode 2 adds the strength reduction factors V1 and alpha CW to the formula for VRD max. The parameter Z can be calculated or assumed as equal to 90% of the effective depth of the section. When these parameters are substituted into the formula for VRD max, It takes the form shown at the bottom of the slide. We can define the lower and upper limit of VRD max depending on the angle of strut inclination. The lower limit is obtained when the inclination angle equals 22 degrees, which is usual for beams loaded by uniformly distributed loads. The upper limit is obtained when the inclination angle equals 45 degrees. In both these formulas for VRD max, the parameter z is assumed to be equal to 0.9 d, when the upper limit of VRD max is smaller than the applied shear force VED, the inclined strut is overstressed. The solutions for this situation include the increase of beam dimensions and the use of a higher class of concrete. When the applied shear force is between the lower and upper limits of VRD max, the inclination angle of the compression struts is between 22 and 45 degrees. In this case, the formula for the inclination angle can be found from equating VRD max and VED. After some algebraic manipulations, it can be found that the inclination angle equals half of the inverse sine of the ratio between VED and the upper limit of VRD max. To derive the formula for the calculation of VRDS, we once again consider the equivalent truss model. The shear force VED developed in the beam under the applied loads should not be larger than the tension force in the vertical tie. The tension force in the vertical ties is resisted by the vertical links. The maximum force VRDS that can be carried by the links equals the design yielding strength of steel times the area of the links. Note that the design yielding strength of steel equals the characteristic strength of steel reduced by the partial safety factor for steel. Since several links are spaced in a beam at a distance s apart over the tension tie width, the total area of links equals the number of links times the area of one link ASW. The number of links can be calculated as the tension tie width divided by the spacing of links, where the tension tie width is assumed as equals z times the cotangent theta. Substituting the expression for the area of links gives the following formula for VRDS. Given that z equals 0.9 d, the strength of one link can be found using the formula for VRDS. Links necessary to resist the applied shear force can be found from the equality of VED and VRDS. The design of links is based on the ratio of the area and the spacing of the links, which can be found using the following expression. The minimum amount of shear links can be found from the ratio between the compression strength of concrete and the yielding strength of steel. When the required amount of links is smaller than the minimum, the latter should be provided in the design. The additional tension force FL applied by the inclined compression struts to the longitudinal tension reinforcement can be found using the equivalent truss model. The compression force developed in the inclined strut due to the applied loads is VED divided by sine the inclination angle theta. The shear force VED is the vertical component, while the tension force FL is the horizontal component of the force in the inclined strut. Therefore, FL and VED are related through the cotangent theta. Eurocode 2 assumes that half of the force FL is carried by the tensile reinforcement provided by the bending design, and the other half of FL is taken into account as an additional tensile force, delta FTD, in the tensile zone. Therefore, additional longitudinal reinforcement is required at any cross-section to resist delta FTD. We'll now consider a few rules introduced by Eurocode 2 into shear design. Where the applied shear force VED is smaller or equal to the design resistance of concrete in shear, VRDC, shear reinforcement is not required by the Eurocodes. However, even when shear reinforcement is not required, minimum shear reinforcement should still be provided. Minimum shear reinforcement can be omitted in members of minor importance, such as lintels. In addition, shear reinforcement is usually not provided in slabs because of the transverse redistribution of loads. Where the applied shear force VED is larger than the design resistance of concrete in shear VRDC, shear reinforcement should be provided. The design of the shear reinforcement should satisfy the condition that VED is smaller than VRDS, which is the carrying capacity of the provided shear links, which is found in accordance with Formula 6.8 in Eurocode 2. Shear design of beams with inclined flanges can account for the contribution of flanges to the shear resistance of the section. And the longitudinal tensile reinforcement should resist additional tensile force, delta FTD, which is caused by shear. In beams subjected to uniformly distributed loads, the design shear force should be checked at not less than a distance d from the face of the support. Shear reinforcement should continue to supports, and shear at supports should not exceed VRD max. When a concentrated load is applied near the bottom of the beam, sufficient vertical reinforcement should be provided to carry the load to the top of the beam, in addition to any reinforcement required to resist shear. In the truss model, the shear force is resisted by the inclined compression struts and vertical tension ties. Since the shear force is largest at the support, and the support is a physical object like a column which has physical dimensions, only the first concrete strut is designed to resist the shear force at the support face. Since the first tension tie is located at least at the distance d from the support, it is designed to resist the shear force corresponding to this location. The procedure for shear design starts with calculating the shear force at the face of the support VEF. Next, the compression resistance VRD max of the first inclined concrete strut is calculated, assuming that the strut inclination angle equals 22 degrees. If VRD max at 22 is larger than VEF, the design proceeds with the inclination angle of 22 degrees. Otherwise, the inclination angle of 45 degrees is assumed and VRD max is recalculated. If VRD max at 45 is larger than VEF, the inclination angle should be found from half of the inverse sine of the ratio between VEF and VRD max 45. If VRD max at 45 is smaller than VEF, the concrete strut is not strong enough to carry the design shear force. The value of VRD max should be increased by increasing the section dimensions or the class of concrete. After checking the stress of the first concrete strut, a tension tie is designed. The shear force VED in the section at d from the support is calculated, and when the shear is low, this distance can be increased to 2.25 d. The resistance VRDC of the concrete in the tension tie is calculated using the following formula. The minimum value of VRDC is also calculated. The expression for VRDC takes into account the effect of concrete compression strength, section size, the amount of longitudinal reinforcement, and the presence of axial force. If the calculated VRDC is smaller than the minimum value is adopted in further design. If VRDC is larger than the applied shear force VED, only minimum shear reinforcement is required. The links required to carry minimum shear are designed. If VRDC is smaller than the applied shear load VED, it is assumed that the entire shear force is carried by shear reinforcement, which is designed based on the ratio between the area and the spacing of one link. The extent and number of links are determined, and this design includes the zone with minimum links. After designing shear reinforcement, its resistance VRDS is calculated. The shear resistance of a beam with vertical shear reinforcement is the minimum value between VRDS and VRD max. At the final stage of the design, the additional tensile force delta FTD in the longitudinal tensile reinforcement is calculated. A design chart can be used for the design of shear reinforcement. This chart is based on the equality of two non-dimensional parameters, ASW times FYK divided by BW times S, and VED divided by BW times D. This is the design chart. As you can see, the chart includes the effects of concrete class, the strut inclination angle, and is divided into three zones. The first zone corresponds to very low shear. In this case, only minimum shear reinforcement is required. The second zone corresponds to low shear. In this case, the reinforcement is designed using the strut inclination angle of 22 degrees, the cotangent of which equals 2.5. And the third zone corresponds to high shear. In this case, the reinforcement is designed using the strut inclination angle between 22 and 45 degrees, where the cotangent of the inclination angle is between 2.5 and 1. The amount of needed shear reinforcement can vary with a shear force. It can be seen in the figure shown here that the changes in shear reinforcement occur over certain length increments. As a result, the resistance of shear reinforcement increases in steps, and in some places it can be smaller than the applied shear force. In regions under uniformly distributed load, the shear force can be calculated in length increments as the lever arm Z times the cotangent of the strut inclination angle theta. The smallest value of the shear force in the increment is used in the reinforcement design. The shear reinforcement ratio is calculated based on the beam width and spacing of links and cannot be smaller than the minimum value. In designing the extent and number of links, the spacing requirements should be considered. The spacing of links, both in the longitudinal and transverse directions, should be smaller than 0.75d. The additional tensile force, delta FTD in the longitudinal reinforcement, is calculated depending on the applied shear force VED and the strut inclination angle. The total force in the longitudinal reinforcement is obtained by adding delta FTD to the force developed in the reinforcement due to bending, where the latter is obtained by dividing the bending moment in the section by the lever arm. To understand the effect of the additional tensile force and curtailment requirements for reinforcement, we consider a diagram showing the envelope of tension force in the longitudinal reinforcement. This is the curve showing the envelope of tension force developed due to hogging bending moment in the end span. This curve is offset by the additional tensile force. This offset is obtained by moving the points of the curve vertically by delta FTD. Alternatively, this offset can be obtained by moving the points of the curve horizontally by the distance A1. To be able to resist the tension forces, the steel bars of the longitudinal reinforcement should extend by the anchorage length LBD beyond the envelope of tension forces. Due to limited number of bars, the envelope of forces in the longitudinal reinforcement has several steps. The same rules apply in the hogging areas above internal supports. Sufficient reinforcement should be provided at all sections to resist the envelope of the tensile force. This should include the effects of inclined cracks in webs and flanges. The offset of the tensile force envelope should be performed using the additional tensile force delta FTD or the distance A1, where A1 equals half the lever arm Z times the cotangent of the strut inclination angle theta. For members without shear reinforcement, delta FTD may be estimated by shifting the moment curve by a distance of A1, which equals the effective depth of the section D. Thanks for sticking around for some vertical shear. Join me next time when we discuss transverse shear.